Hello NET aspirants. Welcome to CSIR NET Atomic and Molecular Physics series. Question number 1. The charge density of the electron cloud of a hydrogen atom is given by ρ, where A is some characteristic length. The potential energy due to the interaction between the proton sitting at the origin and the electron cloud is given by. Here charge density is given, so we will calculate the potential. Now potential at the center, that is V of 0, is equal to 1 upon 4 pi epsilon naught integration rho of r upon mod of r d cube r. The potential energy of the proton in this potential, that is U, is equal to charge on the proton, which is E, into the potential. So this will be equal to E upon 4 pi epsilon naught integration rho of r is minus E upon 8 pi a cube exponential minus r by a, and this will be 4 pi r square dr, r taking values from 0 to infinity. So solving this, will get minus e square, then 4 pi 8 pi, so it will be 8 pi epsilon naught a cube integration 0 to infinity e raised to minus r by a r dr. In the denominator we also have r here, so it will be r dr. So this is the potential energy. We just have to solve this integration. So this will be equal to U is equal to minus e square upon 8 pi epsilon naught a cube. So U into V, so r into e raised to minus r by a minus 1 by a minus integration of this, so minus r by a upon minus 1 by its square du by dr, then dr. So 0 to infinity. If you put infinity, this will be 0. 0, first term will be 0, second term will give us a square. So minus e square upon 8 pi epsilon naught a cube into a square. So this is equal to minus e square upon 8 pi epsilon naught a, which is option 4. Consider a laser cooling experiment where atoms are slowed down by inelastic process of absorption and subsequent emission of photons. If light of wavelength 776.5 nanometer is used to slow down potassium atoms, mass number 39, with initial speed 130 meter per second, the number of such absorption and emission cycles needed to bring the atoms to rest is closest to. Now here, let's calculate momentum of those photons. So that will be equal to h by lambda, and momentum from those potassium atoms, that will be equal to mass into velocity. So mass will be 39 into mass of one proton into v. So the number of such absorption and emission cycles, that will be equal to this momentum upon momentum of photon. So that is 36 into 1.67 into 10 to the power minus 27 into velocity is 130 upon, we have p is equal to 6.63 into 10 to the power minus 34 into lambda, which is 776.5 into 10 to the power minus 9. So from here n will be 9916.36, which is roughly 10 to the power 4. So here option 4 is correct. Next question. An atom is subjected to a weak magnetic field B is equal to 0.1 Tesla. The spectral line of wavelength 184.9 nanometer corresponding to a Z is equal to 1 to Z is equal to 0 transition splits into 3 components. The highest and the lowest components are separated by 3.2 into 10 to the power minus 4 nanometer. The magnetic moment of the atom in Z is equal to 1 state is. Now here delta E is equal to highest and lowest, so delta E1 minus delta E2. So the corresponding energies are Gj, Mj, mu b, b. So we'll write it. So we'll have here G for j is equal to 1 into mu b, b, minus, for the lowest it will be minus G for j is equal to 1 mu b, b. So this is equal to 2 into G for j is equal to 1 mu b, b, where G is Lagrange factor and mu b is Bohr's magneton and b is the external magnetic field. And also we have delta is equal to Hc by lambda square delta lambda. So we will equate these two equations. So we have Hc by lambda square delta lambda is equal to 2 G for j is equal to 1 mu b, b. So from here G for j is equal to 1 is equal to Hc delta lambda upon lambda square into 2 mu b, b. So G for j is equal to 1 is equal to H is 6.63 into 10 to the power minus 34 into C is 3 into 10 to the power 8. Delta lambda is 3.2 into 10 to the power minus 4 minus 9. So minus 13 upon lambda square, which is 1.849 into 10 to the power minus 7 square into 2 into mu b is 9.274 into 10 to the power minus 24 and b is 0.1. By solving this, we'll get G is equal to, this is equal to 1.003. Now magnitude of magnetic moment is equal to Gj mu b j under root jj plus 1. And this is for j is equal to 1. So mu is equal to 1.003 into root 2 mu b. In the units of Bohr magneton we want, so root 2 into 1. So root 2 is 1.414. So option 3 is correct. Next question. In the rotational vibrational spectrum of HCl, the first R branch line and the first P branch line are observed at these wave numbers. The equilibrium bond length of this molecule would be closest to. First we will calculate rotational constant. B is equal to, it will be nu R minus nu P upon 4. 4 because it is first branch line. This is equal to 2906 minus 2865 by 4, which is equal to 10.25 centimeter inverse, which is 1025 meter inverse. That is value of B. Now B is also equal to H upon 8 pi square Ci. So from here I is equal to H upon 8 pi square Cb, where B is rotational constant, I is moment of inertia, and I is also equal to mu r square. So if we calculate I and mu, we can get R. So from here we can calculate I. So I is 6.63 into 10 to the power minus 34, 8 into pi square into 3 into 10 to the power 8 into 1025. So from here I is equal to 2.74 into 10 to the power minus 47, and mu is reduced mass. So that is mh mcl mh mcl plus mcl. So that is 1 into 35 upon 1 plus 35, which is equal to, and into mass of 1 proton, so into 1.67 into 10 to the power minus 27. So this will be value of mu, which is 1.6138 into 10 to the power minus 27. Now moment of inertia I is equal to mu into r square. So r is equal to under root I by mu. So r is equal to under root 2.74 into 10 to the power minus 47, 1.6138 into 10 to the power minus 27. This is equal to 1.3 into 10 to the power minus 10 meter, which is 1.3 angstrom. So option 2 is correct. So these were all the questions from Atomic and Molecular Physics part from CSIR NET July 2025 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.